In the early hours of May 14, 1918, a vessel that defied every established category of naval classification was creeping through the darkness toward the Austro-Hungarian naval base at Pola on the northern Adriatic coast. She displaced approximately 8 tons. She was approximately 5 meters in length. She made approximately 4 knots when her electric motors were running, which was almost inaudibly quiet compared to any gasoline or diesel-powered vessel. She carried 2 torpedoes, and fitted along her hull, wrapping under her keel and extending to both sides in a configuration that naval architects had never previously attempted on a seagoing vessel, were caterpillar tracks, steel tracks. The kind of tracks that drove a tank across the trenches of the Western Front, now bolted to the bottom of a boat, so that the boat could crawl over the steel anti-torpedo nets and harbor booms that the Austro-Hungarian Navy had strung across every approach to its fleet anchorage. Her name was Grillo. The word means cricket in Italian, which was not a martial name, but it was descriptive. A cricket jumps. The Grillo was designed to jump. She was the most mechanically peculiar vessel to participate in the First World War, in a conflict that had produced some of the most mechanically peculiar vessels in the history of warfare. And she was the product of a specific problem in a specific theater that the Italian Navy had concluded could not be solved by any conventional means available to it. She was also, by the time she reached the boom at Pola in the early hours of May 14th, making more noise than anyone had planned for. The specific problem that produced the Grillo was the strategic situation of the Adriatic Sea in the First World War. The Adriatic was a long, narrow body of water, approximately 800 kilometers from the Strait of Otranto in the south to the head of the Gulf at Trieste in the north, with Italy on its western shore and the Austro-Hungarian coastline of Croatia, Dalmatia, and Istria on its eastern shore. The Austro-Hungarian Navy, which was a serious and capable force with modern dreadnoughts and a well-trained officer corps, based its fleet primarily at Pola, at the northern end of the Istrian peninsula, and at Cattaro, a deeply sheltered harbor on the Dalmatian coast to the south. From these bases, the Austro-Hungarian fleet threatened the Italian coast, could interdict Italian shipping in the Adriatic, and could conduct raiding operations against the Albanian and Italian coastal positions that the Allied armies depended on for supply. The Italian Navy was numerically superior to the Austro-Hungarian fleet in most categories of warship, and had modern dreadnoughts that were competitive with the Austro-Hungarian capital ships. But naval power in the Adriatic was not determined primarily by the relative strength of the battle fleets, because the Austro-Hungarian bases were so well protected that bringing the fleet action that would allow Italian numerical superiority to be decisive was essentially impossible without first neutralizing the defenses of those bases. Pola in particular was protected by a combination of natural geography, shore artillery, minefields, submarine netting, anti-torpedo booms, and patrol forces that made a direct naval assault prohibitively costly. The geography of Pola Harbor amplified these defensive advantages. Pola sits at the end of a long, narrow bay on the western coast of Istria, with the harbor mouth protected by a series of islands and peninsulas that created natural choke points where defensive installations could be concentrated. The Austro-Hungarian engineers had exploited this geography thoroughly, constructing shore batteries on the commanding heights, laying minefields in the approaches, and stretching a system of anti-torpedo nets and steel booms across the harbor entrance that was designed to prevent exactly the kind of small boat torpedo attack that the Italian Navy was known to favor. The Italian Navy's tradition of torpedo boat operations and small craft raiding was well established before the First World War and had been reinforced by the specific character of Adriatic naval operations since August of 1915, when Italy entered the war. The Italian MAS, the Motoscafo Armato Silurante, or Armed Torpedo Motorboat, was a small, fast vessel that had achieved several notable successes against Austro-Hungarian shipping and warships through the audacious use of speed and surprise. Commander Luigi Rizzo and his MAS crews had demonstrated that small boats operating at night could penetrate defended anchorages and deliver torpedo attacks against targets that conventional warships could not approach. In June of 1918, a MAS attack would sink the Austro-Hungarian dreadnought Viribus Unitas with the loss of the fleet commander, Admiral Miklos Horthy de Nagybanya. But the MAS boats, fast and capable as they were, could not get through the boom defenses at Pola. The anti-torpedo nets were suspended from the boom cables and extended deep enough below the surface to prevent any conventional vessel from passing beneath them. The boom cables themselves were steel wire of sufficient strength to stop or severely damage any fast boat that attempted to ram through them. The mines and patrol vessels around the boom prevented any approach that could allow the boom to be cut or removed. The polar anchorage was, against any conventional form of attack, genuinely and frustratingly impenetrable. The Italian Navy's response to this impenetrability was to ask whether a boat could be built that did not need to pass through the boom or under it, but over it. The question was not absurd on its face. The anti-torpedo booms at Pola and similar harbors were designed to stop boats that moved through the water in the conventional manner, displacing water, propelled by propellers, unable to move in any direction except those that water resistance allowed. A boat that could move across the surface of the boom, climbing over the obstacle rather than attempting to pass through it or beneath it, would defeat the entire defensive concept. The boom's designers had not planned for a vessel that could treat their obstacle as a ramp rather than a barrier. The mechanical principle required to accomplish this was not, by 1917, as exotic as it might have seemed. The tank, introduced on the Western Front by the British in September of 1916, had demonstrated that caterpillar tracks could move a large, heavy vehicle over obstacles that wheeled vehicles could not traverse. The track principle relied on an endless loop of articulated metal links that distributed the vehicle's weight over a large contact area and provided traction by gripping the surface beneath the track, even on very irregular terrain. A tracked vehicle could climb over trenches, cross wire entanglements, and ascend obstacles that would stop any wheeled or legged vehicle. If the track principle could be applied to a tracked boat could climb over a boom the way a tank climbed over a trench parapet. The engineering challenge was substantial. A boat is not a tank. It operates in a medium, water, that exerts forces on the hull in directions that have no equivalent in the forces experienced by a land vehicle. The tracks that would allow the boat to climb over a boom had to be positioned to provide purchase on the boom cables and net structures, which were not the solid ground that a tank track was designed to grip. The tracks had to be retractable, or at minimum inoffensive to the boat's normal operation in the water, because a boat running its tracks continuously would create drag and noise that would negate the stealth that made the entire concept viable. The propulsion system had to be quiet enough to allow the approach of the target under cover of darkness without alerting the patrol vessels that guarded every major Austro-Hungarian base. The design that emerged from the Italian naval engineering establishment was the work of the engineer Attilio Bisio, working with naval officers who had specified the tactical requirements, and it represented a genuine novelty in the history of small craft design. The Grillo-class boats were approximately 5 meters in length, with a beam of approximately 1.5 meters. Their displacement of approximately 8 tons meant they were substantial enough to carry the caterpillar track system and the torpedoes that were their reason for existence, while remaining small enough to be operated by a crew of 4 men and maneuverable enough to navigate the approaches to a defended harbor. Their electric motors, powered by storage batteries, produced approximately 4 horsepower, giving them a maximum speed of approximately 4 knots in normal operation, and the all-important characteristic of near silence. An electric motor produces no exhaust, generates very little mechanical noise in normal operation, and leaves no wake visible from a distance in the way that a gasoline engine's exhaust does at night. The caterpillar tracks were fitted on both sides of the hull and under the keel, driven by an auxiliary motor that could be engaged when the boat reached the boom. The track configuration allowed the boat to approach the boom in the water, engage the tracks when contact with the boom structure was made, and then use the traction of the tracks on the boom cables to pull itself forward and upward, climbing over the obstacle in the manner that its designers had envisioned. The torpedoes, 2 in number, were carried externally in launching cradles that allowed them to be fired while the boat was still in the water on the far side of the boom. 4 boats of the Grillo-class were built. The lead vessel, the Grillo itself, was the one selected for the first operational trial against Pola in the spring of 1918. The mission was planned and prepared with the care that a first operational use of a genuinely novel weapon required. The approach route was studied from aerial reconnaissance photographs. The layout of the boom defenses was mapped as completely as the available intelligence allowed. The timing of the patrol vessel's circuits around the harbor entrance was observed and factored into the plan. The crew, 4 men under the command of Lieutenant Orfeo Divisione, trained on the Grillo's systems and on the specific technique of climbing the boom until they were as confident in the procedure as practice could make them. The mission was launched on the night of May 13th to 14th, 1918. The Grillo was transported to a position outside Pola Harbor by a supporting vessel and then slipped into the water to make her own approach. The electric motors were engaged and the boat moved toward the harbor entrance at her maximum speed of 4 knots, which was barely faster than a man could walk. The approach took hours. The crew sat in the cramped hull of the boat, listening to the sounds of the harbor, watching for the lights of the patrol vessels, waiting for the boat to reach the boom. The problem became apparent when the Grillo engaged her caterpillar tracks. The designers of the Grillo had solved the engineering problem of building a boat that could climb over a harbor boom. They had not fully solved the acoustic problem of how to do so quietly. The caterpillar tracks, metal links on metal drives, contacting the steel cables and net structure of the boom, produced a noise that was audible at distances considerably greater than the designers had anticipated or that the crew had experienced in their training exercises. The specific character of the noise, a grinding, clattering rattling that was quite different from any of the other sounds of a working harbor, was exactly the kind of unusual sound that the patrol crews and shore watchers were trained to notice and investigate. The Austro-Hungarian defenders at Pola heard the noise. The patrol vessels responded. Before the Grillo could complete her crossing of the boom and get into position to launch her torpedoes at the Austro-Hungarian fleet inside the harbor, the defenders had identified the source of the disturbance and were converging on the boat's position with searchlights and weapons. Divisione and his crew found themselves caught on the boom, the caterpillar tracks still engaged, unable to retreat back into the open water or to advance quickly enough to escape the rapidly closing patrol vessels. The Grillo was captured intact, along with her 4-man crew. This was, from the Italian Navy's perspective, the worst possible outcome in one specific and significant sense. The capture of the boat gave the Austro-Hungarian technical staff a complete and functional example of the caterpillar track system and of the design principles that had produced it. The Austro-Hungarians, understandably curious about the strange vessel that had been caught trying to climb over their harbor boom, examined it thoroughly and published the technical details through their naval intelligence network. The information reached German naval authorities, who found it interesting enough to be filed in their technical records, and through various channels eventually became available to naval engineers in other countries who were working on similar problems of harbor penetration. The operational failure at Pola did not end the Grillo program or the Italian Navy's commitment to the concept. 3 more boats of the class were built and prepared for operations. A second attempt against Pola was planned and executed in the autumn of 1918, by which time the Austro-Hungarian Empire was in the final stages of its collapse, and the strategic situation had changed dramatically. The second Grillo operation, conducted in September or October of 1918, did not succeed either, though the reasons for its failure are less clearly documented than the failure of the first attempt. The war ended with the armistice of November 3, 1918, which included among its provisions the surrender of the Austro-Hungarian Navy before the Grillo-class boats could be employed again. The captured Grillo had, in the meantime, been examined not only by Austro-Hungarian naval engineers, but also by Austrian military officers who recognized that the caterpillar track concept had potential applications beyond the specific problem of harbor boom crossing. The idea of a small boat that could use tank tracks to traverse obstacles had implications for amphibious warfare that went beyond the immediate tactical context of the Adriatic. An amphibious force that could land vehicles capable of moving both in water and on land, transitioning between the two environments without stopping, would have operational capabilities that purely seagoing or purely land forces could not match. The tracked amphibious vehicle concept, which would eventually produce the landing vehicle tracked that carried American Marines ashore on Pacific atolls in the Second World War, was in some genealogical sense related to the Grillo, though the specific lineage of ideas is more complicated than a direct descent would suggest. The context of Italian naval raiding operations in the Adriatic in which the Grillo operated is important for understanding why such an apparently impractical vessel was built, and what it represented in the broader development of naval special operations. The Italian Navy's investment in small boat raiding and torpedo attacks during the First World War reflected both the specific geography of the Adriatic, which favored the kind of surprise attack that small, fast vessels excelled at, and the specific culture of the Italian Navy's officer corps, which had produced a generation of officers who were willing to attempt operations that conventional naval thinking would have dismissed as impossible. The tradition of Italian naval raiding that the Grillo represented would continue into the Second World War in the form of the 10th Mars, the 10th Assault Vehicle Flotilla, whose operators conducted some of the most audacious and effective small boat raids of that conflict. The 10th Mars attacked Alexandria Harbor in December of 1941 using a version of the human torpedo, the maiala or pig, in which frogmen riding a slow-moving underwater vehicle attached explosive charges to the hulls of British warships. The attack damaged the battleships HMS Valiant and HMS Queen Elizabeth, severely enough to put both out of service for extended periods, one of the most cost-effective naval attacks of the entire war in terms of damage inflicted relative to resources expended. The conceptual lineage from the Grillo-class boats through the maiale operators of the 10th Mars to the combat swimmer traditions of modern naval special forces is traceable, though it runs through multiple technical transformations along the way. The specific lesson that the Grillo's failure at Pola was most frequently cited as teaching was the acoustic lesson, that any mechanical system operating in the vicinity of enemy sentinels would be heard if it generated noise beyond a certain threshold, and that the threshold was lower than engineers working in controlled conditions typically anticipated. The noise produced by the caterpillar tracks on the boom cables had been observed in practice during training, but the training exercises had apparently not replicated the specific conditions of a harbor approach, where every unusual sound was being actively listened for by alert personnel who had been trained to recognize and respond to exactly the kinds of sounds that the Grillo produced. The gap between the noise level observed in training and the noise level that proved tactically fatal at Pola was a lesson about the relationship between engineering performance in controlled conditions and operational performance in contested ones that naval special operations planners would need to learn repeatedly in different forms over the subsequent century. The acoustic vulnerability of the Grillo was not the only technical limitation that the Pola operation exposed. The boat's speed of 4 knots meant that the approach to the harbor had taken most of the available darkness hours, leaving the crew exhausted by the time they reached the boom and reducing the time available for the actual climbing operation. The physical endurance demanded of a small crew operating in a cramped vessel for many hours of slow, tense approach was a factor that the planners had not fully accounted for in their mission timing. The psychological strain of the approach, knowing that detection at any moment would end the mission and potentially the crew's lives, was an additional variable that no engineering analysis could capture. The specific character of the failure also illuminated a more general truth about the defense of fortified positions in the context of the technological arms race that the First World War had stimulated across every domain of warfare. The Austro-Hungarian defenses at Pola had been designed by engineers who were trying to anticipate the threats that the Italian Navy was most likely to bring against them. And they had designed them well against the threats they could anticipate. They had not anticipated a tracked boat. The Grillo represented an attempt to exploit the gap between what the defenders had designed against and what was actually possible given the state of mechanical engineering in 1918. This dynamic, the attacker attempting to find approaches that the defender's design did not account for, and the defender attempting to close the gaps that the attacker had found or might find, was and remains the fundamental dynamic of contested military access. The Grillo-class boats were an expression of creative problem-solving in the face of a tactical obstacle that conventional means could not overcome. Their failure at Pola was not a failure of the problem-solving approach, but a failure of one specific implementation of it, an implementation that turned out to have a critical acoustic vulnerability that the defenders were able to exploit. A quieter mechanism for the same climbing operation, had such a mechanism been feasible with the materials and manufacturing capabilities of 1918, might have produced a very different outcome. The 4 Grillo-class boats that were built survived the war in various states. The captured Grillo remained in Austro-Hungarian and then Yugoslav hands after the war and was eventually scrapped. The other 3 were returned to the Italian Navy and presumably scrapped in the demobilization that followed the armistice. No example of the type survives in any museum collection. The design drawings and technical documentation of the class are preserved in Italian naval archives, and the operational records of the missions, such as they are, have been examined by historians of Italian naval raiding operations and of early special operations warfare more broadly. The Grillo is remembered, to the extent that it is remembered at all, as a curiosity, an example of the kind of highly specific, highly improvised engineering that the operational pressures of the First World War forced on every major navy. The curiosity is justified, but it understates what the Grillo actually represented. She was not merely a mechanical curiosity. She was the product of a genuine tactical problem, a creative and technically competent attempt to solve it, and an operational test that produced real information about the limits of the solution. The information was that the acoustic signature of the climbing mechanism was too large to be concealed from alerted defenders in a harbor environment. This was specific and useful information that could not have been obtained without building the boat and trying it, and it was information that shaped the subsequent development of small boat raiding techniques in ways that are difficult to trace precisely, but that almost certainly influenced the Italian Navy's approach to the problem of harbor access in the Second World War. The men who built the Grillo and the men who operated her were working at the edge of what was technically possible in 1917 and 18, attempting to combine technologies that had never been combined before in a configuration that had never been tested in operational conditions. The caterpillar track on a boat was not a ridiculous idea. It was a reasonable extrapolation from the demonstrated capabilities of tracked vehicles on land to the specific problem of a barrier that blocked waterborne approach. The fact that the extrapolation failed in its first operational application, for reasons that a more thorough acoustic analysis during the design phase might have anticipated and addressed, does not change the fundamental reasonableness of the idea. The Grillo sat on the boom at Pola in the early hours of May 14, 1918, her caterpillar tracks grinding against the steel cables, her crew listening to the sounds of approaching patrol vessels, unable to move forward or back quickly enough to escape. 4 men in a 5-meter boat that was part vessel, part tank, part engineering experiment, caught in the act of attempting the impossible, which they had nearly made possible. The noise gave them away. It was the gap between the design and the reality, between the training exercise and the operational environment, between what the engineers had calculated and what the defenders could hear. Naval Special Operations have been navigating that gap ever since, with better tools and better information and better understanding of acoustic signatures and defender alertness and the relationship between engineering performance and operational performance. The Grillo-class boats were among the earliest vessels to map that gap in its specific application to harbor penetration, and they mapped it at the cost of 1 captured boat, 4 captured men, and 1 operation that failed at the last possible moment before success was within reach. Lieutenant Divisione and his 3 crewmen spent the remainder of the war as prisoners of the Austro-Hungarian Empire, which ceased to exist approximately 6 months after their capture. The Grillo went into the technical archives of the victors. The lesson she taught went into the accumulated experience of naval special operations, where it has been applied and reapplied in different forms across more than a century of attempts to penetrate defended harbors, cross-defended beaches, and deliver weapons to targets that conventional naval power could not reach. She was a cricket. She was designed to jump. She almost did.